Hello and welcome to physics video Waves.4a, beat frequencies and Doppler effect. In this video we are going to look at two events that occur when we have sound waves that are interfering with each other. We're going to start with beats and move on to Doppler effect. When two or more sound waves are traveling through the same space, they interfere just like other types of waves do. So let's take a look at these two waves, y1 and y2. They have the same amplitude, but slightly different frequencies. When they interfere, there's going to be a unique resultant wave created that will vary with time, as we can see with the wave on the bottom, y1 plus y2. The red one, which is y2 in the middle there, has a slightly higher frequency than the purple one at the top. So as the waves start, they are in phase, and the resultant wave, y1 plus y2, is going to be their amplitudes doubled because they have the same amplitude, so the resultant will be twice the amplitude. However, as time goes on and the waves no longer line up, the resultant wave starts to change. As we can see, the amplitude decreases as the waves get farther and farther out of phase, until we get to the center of the picture, where y1 and y2 are completely 180 degrees out of phase with each other. And at that point, they cancel each other out, and we have total destructive interference. Then, from being 180 degrees out of phase, they slowly get back into phase until we get to the far right side where they're in phase again, and we have, again, twice the amplitude there. The green and light blue lines that go around the resultant wave of y1 and y2 is called the envelope wave. This envelope wave is what sounds like beats. So it will be louder and then get softer and then get louder and then get softer according to the frequency of the green line here. And the frequency of the envelope wave is easily determined by subtracting the frequencies of the waves that make it up. The frequency of y1 plus y2 is what we call the beat frequency. It is simply the absolute value of the frequency of y1 minus the frequency of y2. Depending on the differences, these beats are going to sound like whoa, 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 or it could be a longer, drawn-out one. Whoa, 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 whoa. The closer they are in phase with each other, or the closer the frequencies are to each other, the longer drawn-out you're going to have. So let's take a look at a gizmo where we'll see how these actually combine to make the beat frequency. All right, so here we have sound A and sound B, and at the moment they have the same frequency, so they're just going to sound like one note. But if I move this frequency, let's say sound A now has a frequency of 441 and sound B has a frequency of 440, and there's sound A on the screen. There's sound B just about on top of each other. The addition of the two, and now I'm going to add in the sound envelope here, the darker blue lines at the top. So if we go ahead and play this, you can see how they get a little bit out of phase as we go, and you can hear the beats going on. Didn't hear much of a beat there because they're so close to each other. Went wow, 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 wow. If we zoom out for a minute, you can see that this is the beat frequency. Blue outline of the green wave in the center shows us the beat frequency. Let's zoom back in a little bit. And let's take a look at what happens if we change the frequency beats again. Let's make it out to 5. And we'll play them again, and we can see how this looks and sounds differently. So you can see here that the beats were much closer together. The frequency of the beats were considerably smaller than before. Because the beat frequency is larger now, it's 443 minus 438, or it's 5 hertz as opposed to being the 1 hertz before. So again, you have an envelope wave on the outside of the blue, and then you can see that as they get farther and farther out of phase, the envelope wave gets smaller and smaller until you get to the point where there is no envelope wave, its amplitude is 0, and then it grows bigger again. I will throw that gizmo into the class so you can play with it some more. The next thing I want to talk about is called the Doppler effect. When the source of the sound is moving relative to the observer, some strange things occur because the source continues to send out waves at the same frequency as it's been producing them. But now that it's moving either in the direction of the wavefront or in the opposite direction of the wavefront, the wavelengths of the waves change. For example, if we look at this fire truck. Here, picture A, we have the fire truck that's sitting at rest. We have somebody in front of it and somebody behind it, and they hear the same pitch sound because the wave fronts are all getting to them. It's at the same time, and they are moving with the same speed, with the same frequency. The wavelengths are the same. However, in picture B, as the fire truck starts to move forward, and it continues to emit sounds, now rather than the wavelength being this, the wavelength decreases dramatically because new sound waves are being produced as it's moving forward. So the initial sound waves, which are traveling outward still, and now being joined with the new sound waves that are being produced from wherever the fire truck is. Similarly, in the back, the wavelength is getting longer because now the source of the wave is moving away from you, the observer, and the result is that it's taking more time for the wavefronts to travel. So when the truck starts moving, the person on the left receives waves at a lower frequency, and the person on the right hears a higher frequency, whereas their wavelength has decreased, but the wavelength over here has increased. Now, these are apparent wavelengths of the waves. The waves being produced by the truck are still the same. They still have the same frequency and wavelength, but according to what's being observed. So rather than calling them F and lambda, we put a prime to indicate that these are the observed wavelengths and the observed frequencies. So if we could figure out the change in wavelength, we can figure out the change in frequency. So let's take a look at the B situation for a minute. We're going to look at two wavefronts only. We can do this by saying, all right, at point 1, this is where the truck was to begin with, and it emitted a wave, and that wave is traveling through space to the right. Then the fire truck starts moving. So the fire truck is moving to the right. At the time we get to point 2, the next crest is emitted. So the frequency of the wave is such that the truck can go from point 1 to point 2 in a wavelength. Well, by the time the truck gets to point 2, the very first wavelength, the very first crest, gets over here to the far right. The next wavelength that's just being emitted is emitted at 2. And that then becomes our new wavelength, our lambda prime. The distance that the source travels is, of course, equal to the velocity of the source times capital T. In this case, capital T is equal to the period of the wave because we are looking at crest to crest. So this T is the period of the wave. So in order to figure out what lambda prime is, we already have an idea that it's dependent on the speed of the source. It's also dependent on the direction in which it is moving compared to the observer. So the change in wavelength can be found by doing a little bit of mathematical manipulation. The apparent wavelength, lambda prime, is the distance that the wave traveled minus the distance the source traveled. So the distance the wave traveled is just the original wavelength, lambda. The distance the source traveled, however, is vt, the velocity of the source times the period of the wave. Well, remember that period is 1 over frequency, and that v is equal to f lambda. So 1 over frequency would be lambda over v. So our apparent wavelength is our original wavelength minus the speed of the source times the original wavelength over the speed of sound. Well, we have lambdas in both of them, so let's pull that out a little bit, and we can say that the apparent wavelength of our wave when the source is moving towards the observer is lambda times 1 minus v source over v sound. This is the first way to look at the Doppler effect. If the source is moving towards the stationary observer, things are one way. If the source is moving away from the stationary observer, things are the opposite way. So if we take a look at these two equations, these are equations 12.2a and 12.2b in your book. Notice that the apparent frequency of your observer, from your observer's point of view rather, is the original frequency over 1 minus v source over v sound. We get this by keeping in mind that v is equal to f lambda. And we just had the lambda on the last page. So when the source is moving toward the observer, you have 1 minus v source over v sound in the denominator. If you have the source moving away from the stationary observer, then it's the original frequency divided by 1 plus v source over v sound. The difference between the plus and minus is due to the fact that velocities have direction, so you have to keep that in mind. So in this case, we have the frequency changing, we have the wavelength changing. If the observer is what is moving, then things are a little bit different. In the case of the observer moving and the source of the sound being stationary, the wavelength remains the same, but the speed is different according to the observer. So let's take a look at that. If we have a moving observer, as shown here in our picture, we have a source of a sound. Maybe it's a siren coming towards you and you've moved over as the driver. Then the lambda stays the same in this case, the wavelength, so we need to look at the velocity and the frequency changing. Again, using v equals f lambda as a starting point. And keep in mind that the prime next to the f here and the lambda earlier are indications that these are the perceived wavelengths and frequencies for the observer. So when the observer is moving towards the stationary source, again, using v is equal to f lambda and adding velocities or subtracting velocities depending on which direction you're going in, leads us to f prime is equal to the velocity of sound plus the velocity of the observer times the original frequency over the velocity of sound, which again, we can pull out the v's and make it look a little bit neater so it's in the same format as our lambda previously. And if the observer is moving towards the stationary sound, then we have 1 plus v observer over v sound times the frequency. And if they are moving away, then we have 1 minus the velocity of the observer over velocity of sound times the frequency. So note that when the observer is moving, it is multiplied by the frequency. When the source is moving, it is the frequency divided by that quantity in the parentheses. So that's the biggest difference here for the Doppler effect and looking at the changes in frequencies depending on who is moving. Most of the time, we don't want to have to worry about memorizing 4 different formulas for situations that are very related to each other. So instead, I'm going to give you a combined Doppler equation that looks at all of the different possibilities together as one. This is the combined Doppler equation. It looks pretty ugly, but let's talk through it for a minute. F prime is equal to 1 plus V observer over V sound divided by 1 minus V source over V sound, the entire thing times the frequency. Now, the plus minus, the minus plus here is an indicator of which direction things are moving. You're going to use the top arithmetic functions. So you're going to use the plus and the minus if the observer or the source is moving towards each other. And it doesn't matter which is moving, the observer or the source, because if the observer is not moving, then V observer becomes 0, and the numerator of the large fraction here becomes 1. Similarly, if the source is not moving, then V source becomes 0, and the denominator becomes 1. So it all works out depending on what you're looking at. If you are moving away from the source, if the observer and the source are moving away from each other, then we use the bottom arithmetic functions. So now you just have one equation that you need to remember for the Doppler effect. It takes care of whether the observers are moving towards each other or away from each other, as well as if only one of them is moving and the other one isn't. The key is for you to remember that the top arithmetic functions go with going together, and the bottom go with going away from each other. Next video will be some calculations about how to use the Doppler effect and what to do with beats, and this equation will become more clear to you then, I think. So bye for now.